Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I want to help you solve a systems of equations by not just explaining the process, but actually working through 8 different examples. So you can kind of see what types of problems I'm going to go through. We are going to do this by elimination with either using a multiplier, one multiplier, no multipliers, or 2 multipliers. Let's just do that again. Welcome, ladies and gentlemen. My name is Brian McLogan. Welcome, ladies and gentlemen, my name is Brian McLogan, and in this video, I'm going to help you solve a system of equations by elimination. And I'm going to do that by working through 8 different examples. And the examples that we're going to cover here are going to be using no multipliers, 1 multiplier, or 2 multipliers. So you can kind of see the little variety of the problems we do. And I'm hoping that after we've worked through all of these examples, you'll have a better idea, no matter what type of problem you're given, if you need to solve it using elimination. Now, just to kind of do a quick little roundup, we're not going to be using substitution or graphing. But again, remember when we're looking for the solutions here for these 2 equations, we're looking for basically where these 2 equations are going to match up. So we could always use substitution or graphing as well. But a lot of times elimination is just going to be the easier process for us to solve. And again, just to kind of visually look at this just real quick, if we're looking at a graph, when we graph these 2 lines, we're looking for if there is that intersection point and that xy. That is what we're calling the solution, because whatever xy point that makes both, that is where those graphs intersect, that is going to make both of those equations true. And what I'll do is for these, first example, I'll be able to plug them in, and therefore you can kind of see how that works. And in this first example, a lot of times, when you have a variable with no coefficient, then obviously you could also use substitution as probably be the more, an easier process to go and use. But we're going to focus on elimination. So let's just go ahead and, kind of talk through what is the process. So the main process when you're applying elimination is basically you're combining the 2 equations by either addition or as subtraction. Preferably, I like to always just think of addition, right? You can always write a subtraction problem as you can always write a subtraction problem as an addition. So I always like to just think of addition method rather than doing addition or subtraction and trying to guess which one is going to make sense. So if you think about this, the main thing that we're looking for with our variables, and again, we need to solve for both variables, the a and the b, is we want to eliminate one variable at a time. And to do that, when we add variables, like if I said 2x plus, let's just do this to the side actually. If I said, 2x plus 2x, well, that gives us 4x, right? We combine the coefficients. So what we want to do is we want to combine the coefficients so it gets to 0. And in this case, you can see that, well, that's perfect, right? For a, I have positive 3 and negative 3. So if I add these 2 equations, I end up getting a 0 times a, and 4b minus 2b is going to be a positive 2b. And then I can just add these. So you can kind of do them just kind of vertical addition equals to 6. Now, obviously, 0 times anything is just going to be 0. And a lot of times I won't even write that in there because we'll know that we just eliminated it. And therefore, you can see 2b is equal to 6. Now, just solving using my inverse operations, I'll divide by 2 on both sides. And I get a b. That's not a really good b. I can get b is equal to 3. So that is one solution. And now I need to basically find for a to find the other solution point. So now what I'm going to do is I'm going to take the value b and plug it into either one of those equations. And it doesn't matter which one you do. I would probably stay away from the one with all the negatives because usually students make more mistakes with that. So I'll just plug b into that first equation. So I have 3a plus 4. Instead of writing it times 4 times b, I'm going to write it as 4 times 3 equals 9. So therefore I have 3a, what am I doing? Plus 12 is equal to 9. And now you can see I have a 2-step equation. So I am going to subtract 12. And I can write a 3a is equal to a negative 3. And let's put this over here. Kind of running out of space. 3a equals negative 3, and then divide by 3. So therefore, a is equal to negative 1. Now, in terms of graphing this, is this identified as a solution point? You could think of 1 as a and b. It depends, we're not really graphing. Typically, we're graphing with the x and y terms. But I want you to understand that when a is equal to negative 1 and when b is equal to positive 3, that makes both equations true. And again, we can verify this. We're not going to do this for all the other problems, but we'll do it for this one. Let's go ahead and plug them in and make sure that it works. Equals 9. So if we plug in a is equal to -1 and b is 3, so not 12, let's see if that go ahead and works. Well, 3 times -1 is going to be a -3 plus 12 equals 9. Okay, and I don't need to really simplify. You can see that that works. Now we can plug that in again to the last equation, or the bottom equation. So 3 times -1, I'm sorry, that's a -3 times -1 minus 2 times 3 equals -3. And therefore that becomes a +3. That becomes a -6 equals -3. Okay, so I just want to kind of verify this so you understand those solution points. Obviously, when we're determining with x and y's, a lot of times we're confirming that x and y point. You know, you can look at that by the graph and so forth. But I just wanted you to kind of see that's why these points are so true. When you plug them in for a and b in both equations, they make both equations true. And that's what's so important. You can't just that's why it's so important for when we solve these two variables to have those two equations and use this process. All right, so now let's go and look at this. And you might think, all right, so main idea is we add them. You know, they got to have the same coefficient. And you could also subtract them, as I kind of mentioned. But again, in my purpose, that kind of makes things a little bit more difficult. So I want to add. And if I add these two equations, I would get a 2x plus 3y is equal to 16. Well, that doesn't make it anything easier for me to be able to solve this using elimination, right? I didn't eliminate a variable. So our goal again is to get this to be 0. So we could subtract x minus x to give us 0x, or typically what I like to use is using the multiplier, and this helps us for our more advanced problems. So what I'm going to do is I'm simply going to take that first equation, x plus 2, or sorry, the second equation. Oh, it doesn't really matter. X plus y is equal to 6. Actually, you know what? Let's put this over here. Let's move this over. All right, what I'm going to do is I'm going to multiply this by a -1. So you could do the top or the bottom. It does not really matter which one you do. But when you go ahead and do that, you now go ahead and get a new system of equations. Let's go back to our red. That is going to be x plus 2y is equal to 10 all over a -x minus y equals -6. Now you can see how that's distributed to both of them. And now I can go ahead and use my addition. So now I'm going to add both of those. I'll just put them in parentheses so you can see that addition, like what I did there. And so now I get a 0x. 2y plus y is just going to be a y is equal to 4. So you can see y is equal to 4. And now if I wanted to go ahead and solve for x, I'd go ahead and plug that in. And again, you can plug it into any equation. Typically, you know, the first equation might not be too bad, but let's plug it into the second equation actually in this case. That actually seems better. Before you had to multiply it by before you multiplied it by -1. So now I just have x plus, 4 equals 6. Subtract the 4, subtract the 4. X is equal to 2. Now in this case, we have an x and y, and it kind of a little bit more resembles what we have talked about in terms of, graphing. So a lot of times we'll write those solution points as 2, 4, right? You can write that as a solution point. And again, if you needed to check your work, you could always plug them back in. So those are your kind of two basic examples. When the coefficients are the same, both one's positive, one's negative, just add them. And if they're both positive or both negative, then you're going to want to use a multiplier of -1 to multiply one of those equations. But usually the problem that a lot of students get is when the coefficients are not the same. How do you decide what to multiply by? And so in this case, we are going to... In this case, we're going to look at, we have x and a y. And again, it doesn't matter which one you want to identify first. Sometimes for some problems, it's a little bit easier to choose one variable over the other. And then sometimes it doesn't look like it matters, right? In this one, it looks like they both are just multiplied by 2 and you're going to get rid of the next variable. So in this case, what I'm going to do is, let's just try to eliminate the x here until it becomes more apparent to solve for the second variable. So if I want to get the x, the coefficients of the x to be the same, I would want to multiply by a 2. Now again, I don't want them to be both positive though. Jeez. I don't want them to be both positive because then I have to use a negative multiplier. I want them to be one positive and one negative. So what I'm going to do is I'm going to multiply by a -2. So make sure when you multiply by -2, you're multiplying everything by -2. And now what I get is a negative 8x plus 6y is equal to a negative 20. All right, and then I have an 8x minus 6y is equal to a positive 20. Now, something very, very interesting happens here. When I add them up, I get 0x plus 0y is equal to 0. So basically, I get 0 is equal to 0. So what does that mean? Like, what is the value? You know, we didn't eliminate x. We actually eliminated x and y, and we don't really have a solution. We didn't get an a equals and a b equals. Well, in this case, there's two things that happen. It's either we have a no solution, meaning we have lines that actually never intersect. So we could actually have lines that never intersect. Those are what we call parallel lines. So those are called no solution. They're inconsistent. Or we could have ones that have infinite many solutions, meaning they're actually the same line. So same line. And I'm not going to get into the labeling of like consistent, one solution, infinite many solutions, inconsistent, no solution from there. But we can see that since this is true for all x's and y's, that means no matter what value I plug in for x and y, it's going to satisfy both equations. So if it satisfies both equations, that means both equations have to be exactly the same. So we're just going to write infinite many solution. Okay. All right, let's go ahead and get on to question number 4. So question number 4, again, you know, if we look at the first term, it doesn't seem like 2 and 5 have like an easy multiplier, right? I mean, I can't multiply by 5 by a certain integer to get it to 2, and 2 times 2 is 4, 2 times 3 is 6. So that doesn't seem as easy as 1. So I'm going to move to the second variable now and see if that's maybe a little bit easier. And it is, right? You can see that from -3 to, or to go from 3 to 6, I just multiply by 2. And thankfully, 1 is negative, 1 is positive. So in this case, I'm just going to multiply my top equation by positive 2. I don't need to multiply by negative in the case because I already have a positive and a negative. So by doing this, I get a 10x minus 6y equals negative 6. And then the bottom remains the same. Okay, now I can add. By adding here, I get a 12x. That goes to a 0y is equal to a negative 6. All right, and then divided by 12, I'm going to get a fraction. Cool. X is equal to a negative 1/2. Now, again, just like we did before, take that x and plug it into one of those equations. You could plug it into either one of them, but you know, I wouldn't plug it into this top equation because, you know, 5 times negative 1/2 doesn't really look like a nice number, right? But if I could plug it into this top equation, I can see that the negative 1/2 is going to divide out with the 2. Oops, that's an x. No, yeah, that's fine. So therefore, that goes -1 plus 6y is equal to 0. Add the 1, add the 1. 6y is equal to a positive 1. Divide by 6, divide by 6. Y is equal to 1/6. So not always are our solution points going to be as pretty, you know, as we want them to be, basically being integers. They can be fractions as well because, again, you know, what we're looking for is that solution point, right? We're just looking for where the graphs intersect. They don't have to intersect at rational numbers. They can intersect at fractions, you know, as well. All right, now let's go ahead and take a look at another one here. So this one, now this one looks like it's all the same, right? It looks like those are the same. So, you know, those are multiplied by 2. So I'd say, well, you know, probably going to be a infinite many solutions like that last example. But just be a little careful here. I'll need to multiply here by -2. All right, and when doing that, I get the negative 6x minus 8y is equal to a negative 36. That becomes a positive 6x plus 8y equals 18. And now when I subtract them, though, I get a 0x, you know, plus 0y is equal to a negative 18. So 0 is equal to a negative 18. 0 is equal to negative 18, which is false, right? 0 is never equal to negative 18. So that tells us something that's different. In our case where we had infinite many solutions, no matter what the values were for x and y, it always made both of those equations true. That's why they always lied on the same line. Well, here, it doesn't matter what x is or what y is. These are never going to be the same. When you get a false statement, it doesn't matter what x and y you can choose. They're never going to be the same. So therefore, they're never going to if they're never going to be the same, that means they're never going to intersect. Therefore, you can see that they are going to produce parallel lines. And if you were to graph them, they would produce parallel lines. But we can just write this. We'll just say that is not true. And we'll just write no solution. All right, on to the next one. Now we have some issues. Now these are the ones where students, this is usually when students start to feel comfortable and confident with elimination. The next two examples is where we get to have a little bit of fun, because what we recognize is you just can't multiply one equation by another one to eliminate the x here. What it looks like we're going to have to do is use two multipliers. So we got to find the least common multiple of our two variables, of our two coefficients. So we could find the least common multiple of 4 and 6, or we could find the least common multiple of 5 and 2. Now, it doesn't matter which one you do. Typically, we like to find the least common multiple. It's going to usually be the smaller number just to make things easy. And so if I were to multiply these, 6 times 4, that'd be 24, but it looks like they have a common multiple of 12. And then 5 and 2 has a multiply by 10, and that is their common multiple. So I'm going to use 5 and 10. And also, I like the fact that this is negative and this is positive. Therefore, I can just multiply by numbers that are going to be positive. So the least common multiple here, I was just going to say is 10 between 10y. So again, we want one to be positive, one to be negative, because if we add them together, we want them to get to 0. So what do I need -5 to be to get it to be a 10y or negative 10y? And all we need to do there is just multiply by positive 2. So I'm going to multiply the top equation by 2. And the bottom equation, what do I need to multiply 2 to get it to be 10y? That's going to be a 5. So again, I don't want to overly confuse with this LCM. I'm just not going to put the y in there. I'm just going to say LCM of 5 of 10. And again, you could do both positive or both negative, right? And then subtract them instead of adding them. But my preference is to always add them. So we want one to be positive, one to be negative. Now we have to multiply each equation by all of these numbers. That's why it's like a lot of work. And a lot of people just don't like doing it, right? I mean, it's a lot of multiplying, a lot of work you got to do. But I want you guys to see that I multiplied that 2 times every single term inside the top equation. And then I'm going to multiply this term by everything in the bottom equation. Oh, crap. 48 times 96. I don't remember that. I'm just going to use my calculator. 48 times 5, 240. Jeez. I didn't realize I was going through such big numbers here. So now let's go and add them, though. All right, and by adding them here, we get a 38x. That goes to 0, right? So we don't need to worry about that. And then this becomes 266. Now, if I'm doing my numbers correct, I am hoping that 266 is divided by 38, but I do not know that math off the top of my head, and nor do most students need to know this math off their top of their head. So I would just say use a calculator. Hopefully one's available so you don't have to use longhand work. And you can see that this answer is 7. So 266 divides into 38 7 times. Now you can just plug this in. Again, you can plug it into the top or you can plug it into the bottom. I'll just plug it into the bottom. Doesn't really matter. So therefore I have 6 times 7 plus 2y is equal to 48. You see that this is 6 times 7 is 42. Then I will subtract the 42 on both sides. So I get 2y is equal to 6, and divide by 2, y is equal to 3. Again, this is terms of x and y, so I'm assuming that this is going to be represented here as a solution point where the two graphs are going to intersect each other. All right, last two to go. So number 7, same kind of thing. And again, doesn't matter. You can find the LCM of either one of those. I prefer to do this, this one just for the positive negative, but let's pretend we want to do this. Like, what's the common multiple of 2 and 3? Well, hopefully you recognize it's 6, right? Now, the problem is where a lot of students get in trouble is they're like, well, which one are you going to make negative? And it doesn't matter. It really doesn't. It doesn't matter if this was positive, like when we're adding, it doesn't matter if this was negative 10y and that was positive 10y, or that was positive 10y and that was negative 10y. So just pick. So in this case, I'm just going to make the numerator the negative, just because I want to make that to be positive. No other reason besides that. Actually, you know what? I don't want that to be positive. I want that to be a negative because I want to find the difference here of those when I add them. So I'll make that a 3. Oh, if that's negative, I guess it doesn't really matter, does it? It doesn't. Okay, so let's just do it that way. I'll do the 3 and the negative 2. It doesn't matter. Do it the other way if you like. But let's multiply the 3 times everything. 6x plus 9y equals negative 18. And therefore, this I get a negative 6x plus 8y equals a negative 50. Okay, now we have the same coefficients, one's positive, one negative, right? So if you just multiply by 3 and 2, you'd have to then go ahead and multiply again by a negative value. So that goes to 0x. Here we're left with a 17y. And here we're going to be left with a negative 68. Okay, now obviously, thankfully this one's not as bad. So if I divide by 17, y is going to equal, let's see, 17, that's 34, so that's going to be a negative 4. So now I have my y equals negative 4, and let's go ahead and plug that into either equation. Let's choose the top one this time, just because I chose the bottom last time. It doesn't really matter. Do whatever you really want to do. I don't really see a difference in one equation being, easier than the other. Sometimes you do, so you always want to look for that. But in these two examples, I'm not really noticing anything. I'd probably say, probably actually avoid these operations with the negative. But this isn't too bad. So, okay, so x equals negative 9. And then just for the sake of, since everything was given in x's and y's, I'll have negative 8 and negative 4. Okay, so now on to the last example, which I made some couple corrections here. I have x plus y is equal to 1, and then 2x minus y is equal to 12. So fairly basic if you think about, the whole process. You get to this point, I'm just going to rewrite it, and you say, oh, well, this one's rather easy. I'm just going to go ahead and, add these together. But when you add these together, what you notice here is you get 3x is equal to 13, and 3 does not divide evenly into 13. But that's okay, right? We're still just going to work with what we have here. So typically you could plug it into either equation. I'm going to think that this first equation here is going to be a little bit better. So I'm going to have a 13 over 3 plus y is equal to 1. And then now to solve for this, I need to subtract a 13 over 3 from both sides. Therefore, I'll be left with y is equal to 1 minus 13 over 3. And again, what's important about this is I want students to make sure that they can use our fraction operation. So remember, we can always rewrite 1 as 3 over 3 minus a 13 over 3. And therefore, that's going to leave us with a negative 10 over 3. So now we can write our coordinate point here as 13 over 3, comma, negative 10 over 3. So there you go, ladies and gentlemen. There are 8 examples of how to do how to solve systems of equations by elimination. We worked through ones that include fractions. We worked with ones that have using one multiplier. Ones do not have a infinite many solutions, have two multipliers, ones that have no solution, as well as ones that you just are going to add or subtract to be able to get the answer. So I hope that helped. And if you have any questions, feel free always to comment below, and I'll see you guys on the next video. Cheers.